What is light? Why does it behave as it does? The early struggle to explain light was a war between two models. Sir Isaac Newton's particle model battled Christian Huygens' wave model. As time went by, evidence mounted in favor of the wave model. It was improved and became Maxwell's electromagnetic wave model. It looked like the end for the particle. And then, to the surprise of the entire scientific community, Max Planck, Albert Einstein, and their quantum model gave new life to the particle. The light photon is a powerful new way of looking at an old idea. It helps to explain long-predicted behaviors of light, like pressure. Real particles exert pressure. Newton himself formulated laws of momentum. Which help to explain pressure. The product of a mass and its velocity is known as momentum. If a stationary mass is struck by a moving mass, the momentum is transferred. If we add up the momentum of two masses before a collision and after, the momentum vectors after the collision always add up to those before the collision. In 1923, scientist Arthur Compton showed that photons also appear to have momentum. He used a cloud chamber in which tracks left by atomic particles can be observed. He fired X-rays of known photon energy into the chamber. Occasionally, the stream of X-rays produced the track of an electron. At the same time, Compton discovered that X-rays had been deflected at an angle. The photon energy of these X-rays was reduced. Compton showed that this collision is similar to a collision between two particles, in which momentum is conserved. He calculated from the photon energy that if a photon has momentum, when it interacts with an electron, the momentum is conserved. Compton's demonstration was evidence of the particle-like nature of light. Conservation of photon momentum supports the prediction that light exerts pressure. We can actually see the results of this pressure in the heavens. Scientists generally accept that the photon pressure pushes the tiny particles that form the tail of a comet, so that they always stream away from the sun. Some visionaries have proposed that gigantic sails could catch this photon wind to push spaceships between the stars. And what about other behaviors of light? Can scientists use the photon particle to explain them all? Interference patterns, for example. The wave model nicely explains how constructive interference produces lines of brighter illumination to create distinctive interference patterns of light. Can particles describe the same pattern? Imagine that light is composed of many photon particles instead of waves. Could it be that these particles interact in some yet-to-be-discovered way to produce the interference pattern? Geoffrey Taylor provided a dramatic answer to this question. He set up an experiment which used photographic paper to record interference patterns. This light-sensitive paper gradually records a pattern even if the light is weak. Taylor repeated the experiment, reducing the level of light entering the slits until it took months to produce the pattern, to the point where he calculated that on average only one photon at a time approached the slits. And what was his result? How could the same pattern be explained by particle interaction? With only one photon in the apparatus at a time, no interaction was possible. In spite of the quantum theory and the photon model, we still need the wave model of light to predict just where the photons will strike after passing through a slit. Taylor demonstrated that the particle model cannot provide all the answers. The wave model is still an essential tool for describing the behavior of light. Is one model more useful than the other? That depends at least partly on the kind of electromagnetic radiation. Some forms of electromagnetic radiation are more wave-like. Radio waves, for example, with very long wavelengths, clearly demonstrate wave characteristics, like interference. For example, a radio wave in its reflection can set up an interference pattern. On a car radio, we can often hear this as peaks of intensity and dead spots as we move across the pattern. But it's difficult to detect a single photon of radio radiation. At the other end of the radiation scale is gamma radiation. These wavelengths are so short that it's difficult or impossible to demonstrate interference with slits, no matter how tiny they are. On the other hand, the energy travels in particle-like photons, which are easy to detect as separate clicks of a Geiger counter. Quantum physics and the photon model of energy radiation have changed the face of modern physics. And yet, the electromagnetic wave model is still an essential tool. Today, the two models support each other to provide us with a clear understanding of light.